In this paper, we derive depth normal ambiguities for refractive objects using light ray correspondence. Transparent objects do not have an appearance of their own. They merely distort their surrounding environment. A powerful approach to infer the shape of the object is to study how it interacts with light rays. However, even when we study the problem using light rays, for most objects light rays will bend at least twice, once each upon entering and exiting the object. This makes the reconstruction of the shape a hard problem. We assume that we know the refractive index of the transparent object. With knowledge of an ingoing and outgoing light ray, can we infer the depths and surface normals at the two refraction events? We find depth normal ambiguities for transparent objects. Our results can be stated in the form of two theorems. First, given the surface normal at the first refraction location, we show that the depth is unique. Second, given the surface depth at the first refraction, we show that the normal is constrained to lie on a 1D curve. In the following, we explain the geometric interpretation underlying these two theorems. Assume that we know the surface normal n1 at the first refraction. By Snell's law, we know how light rays changes its direction after refraction. That is, we know O1. However, we do not know where the first refraction happens. Therefore, we can hypothesize different values of the depth. For example, D11 or D12 or D13. If we collect all these hypotheses, we can observe that all possible light rays after the first refraction sweeps through a plane. By intersecting the outgoing light ray with this plane, we can find the location of the second refraction. Thus, we can find the depth corresponding to this particular location. Therefore, we can see that given a surface normal, the depth is unique. However, note that we assume we can find the second refraction location by intersecting the plane with the outgoing light ray. If the light path is coplanar, that is completely lies within a plane, we cannot find a unique intersection. In this case, even given the surface normal, the depth is still unknown. Now we explain the second ambiguity. Given the surface depth at the first refraction, the normal is constrained to lie on a 1D curve. Given the surface depth, the location of the first refraction V1 will be determined. The second refraction will happen along the outgoing light ray. We hypothesize that it happens at V21. Thus we know the light ray direction connecting the first and the second refraction O1, 1. The normal corresponding to this outgoing direction is N11. Similarly, we can assume that the refraction happens at V22. We can also compute the corresponding surface normal N12. The same procedure holds for any point on the outgoing light ray, for example V23. All possible light rays after the first refraction will lie on the grey colored plane. We can see that the normals corresponding to these outgoing direction will trace a 1D curve on the unit sphere. Up to this point, we present the geometric interpretation of the two depth normal ambiguities for transparent objects. These two properties provide insights for sufficient conditions for reconstructing a transparent objects. For example, we will need at least 3 light ray correspondences to reconstruct a surface patch. This can be explained by the depth normal ambiguity. For a surface patch observed in a camera, let's begin by hypothesizing a depth. This will give us a 1D curve of possible surface normals. We can also observe the surface from a different camera view, which gives us a second light ray correspondences, and in turn, a second 1D curve of possible normals. As we can see from the left image, any two 1D curve on the sphere can potentially intersect, and thus it does not allow us to validate the hypothesized depth. However, if we include a third camera view, we can check if the third curve generated intersects at the same surface normal. If they do, then the hypothesized depth is correct. Therefore, we need at least 3 cameras to reconstruct a transparent object. If we further impose a surface model, For example, the object being planar on one side, then we can reconstruct the shape of a refractive object using just a single camera. The idea is that we can generate three light ray correspondences that share the same surface normal. And by looking for a consistent surface normal that validates our hypothesis, we can recover the shape of the object. Here we show a reconstruction result using the planar assumption. Notice how the details of the different facets of the diamond are all preserved. For more details, please visit our lab webpage.